I am Lorenzo Marcucci, and I work at the Department of Biomedical Science in University of Padua. And I will present today our work, the work of our group in the mechanical characterization of the extracellular matrix in human skeletal muscle and its modification related to the ages, to the age. In particular, this is a project which we started a few years ago and is growing, especially because we wanted to merge experimental testing and the numerical modeling, as shown in this slide. I decided instead of presenting all the data that we collected till now, to divide the presentation in two parts. The first one, I will give you the framework in which our project is being developed, and in the second part, I will show you only the latest result that we got, which are probably of more interest for the audience. Okay. So let's start from the concept that, of course, as you know, people, humans in aging, I mean, is losing the effective capability of using force. I mean effective capability because is known, as shown in the figure, but there are a lot of evidence of it now, that of course with age people are losing the ability of producing force in general for daily activity, as shown in the orange drop bars with age. But this drop is not fully explained by the drop of muscle mass, as shown from the blue bars. So, of course, something else must happen in order to fully explain the loss of generating force. And among other, of course, there are a lot of explanation for it, but among other causes, it is becoming more and more clear that a reason may also be the ability to laterally transmit force, in the sense that, of course, usually we do not need just to generate force exactly in the direction of muscle fibers, but we need this force to be applied in the space in different dimension, in different direction. So it's important that the muscle can use the force generated along the axis of muscle fibers also in different direction. So I can make a very short historic background of the idea of lateral transmission of force, because it's relatively recent if we consider the long history of muscle research. We can start from 1983 with the experiment made by Street, where she cut a wall frog muscle, leaving intact only one single fiber, measuring the total tension of this single fiber from hand to hand, and then to measuring the tension activating only that single fibers from one hand to the cutted edge of the muscle. And she shown that the total tension was actually almost the same in the two cases. So the single fiber was able to transmit their own force, not only longitudinally, but also laterally. Another example, which is important for us, because I will take it at the very end, the very last slide of my presentation, was one made by Hui Jing in 1998. He took the ADL from ADL muscle, which is made by 4 heads, and he cut the distal tendon one after the other of the heads, first 1, 2, and then 3, showing that the drop in the total tension was not proportional to the amount of tendons that he were cutting. The drop was not 25, 50, and 75%, showing that even the cutted heads were able to express their own force through lateral transmitting it to the intact muscle. The last experiment, which is more important for us because it includes also the effect of aging, was made by Ramaswamy in 2011, so relatively recently if you want. is very similar to what has been done by Street, but for the wall muscle of rat. And she analyzed the total force first from tendon to tendon, and then from one tendon to the joke put in the middle part of the muscle. So in this way, he was able to put result in a graph like this, where he compared the longitudinal force and the lateral force, showing that in young rats, actually the two forces was standing along a line, which slope was about 45 degrees, which means that more or less the longitudinal force was exactly the same as the lateral force. But when he compared the same data for old and very old rats, then he shown that this slope was smaller and smaller, which means that at the same longitudinal force, the lateral force was always smaller, which is clearly an impaired effect for older rats, in this case, to transmit the force laterally, and then maybe to use it in an efficient way in the daily life. So how the force is transmitted laterally? Of course, depends on several proteins, but we are interested in extracellular metrics, mainly because we can analyze extracellular metrics. In particular, extracellular metrics is important because it is a very intimate properties of muscle. It surrounds single fibers, group of fibers, group of muscle cells, and till the whole muscle. And it is important for us because it has been shown that the extracellular matrix is actually even between single fibers. And we can, with the setup that we have at the Department of Biomedical Science, we can mechanically test the properties of not only single fibers, but also group of fibers. So also including the extracellular matrix. Okay, so with this background, we had in mind this scientific question. So given that the variation in the lateral force transmission through the extracellular matrix may have an important role in the loss of force production with age, how we can quantitatively estimate this role, especially in humans? And at the beginning, we decided to answer to this question through the use of finite element models, because clearly nowadays we can generate finite element models multi-scale structure where the fibers and the extracellular matrix has different meshes and so different material properties, and we can with some effort, numerical effort, also produce the behavior of the fiber, bundles of fiber, a bundle of fibers, and then also of the whole muscle at the microscopic level. But what we need is to put into our model some reliable experimental data for humans. And we discovered at the beginning of our work that there are very few data for humans in this respect to characterize the extracellular matrix at the quantitative level that we need for the finite element models. Okay, I will not show in the next many results from finite element, more from the experimental part, in order to obtain numerical values to include it in the finite element models. And we approach this with the following setup. We passively stretch fibers and bundle of fibers stepwise, elongating it and analyzing at each step the passive tension after the dynamic relaxation and the length of the sarcomere length at any step, both, as I said, for fibers and bundle of fibers in human vastus laterali, in young, in average 21 years old, and elderly, 76 years old, human subjects, in the physiological range of sarcomere length from 2.5 to 3.3. Okay, so I can go directly to the results here, which probably is of some interest for the audience. First, show the raw data about the tension measured on the bundle for elderly on the left and for young on the right subjects. Clearly, the tension measured on the bundles is higher, much higher actually than the one observed on the fibers. Okay, I'm sorry, on the fibers. We are speaking about tension, so not force. Of course, force is higher because the bundle is also bigger, but we are dividing it to the cross-sectional area of the specimen that we are analyzing. So what we can say is that the extracellular matrix clearly exert an extra passive tension respect to the single fibers, because we cannot completely explain the passive tension observed in the bundle only with the passive tension generated by single fibers, if you want, by titin, just to simplify the description. Going to the statistical analysis in this single figure, we collect all the data for young in blue colors and elderly in red colors, for fibers in pale colors, and for bundles in dark colors. So again, we can see that both from in the deep color, considering the comparing the deep colors to the pale colors in blue and red, so in young and old, there is a statistical difference in this extra tension generated by extracellular matrix. We did not observe, as some other groups, any difference in the passive tension generated by single fibers, but we did observe a significant difference in the passive tension generated in elderly and in young subjects. Elderly generate a higher passive tension at the same sarcomere length level. Now, I am a material engineer. Now we wanted to separate the so-called extrinsic properties and intrinsic properties of this higher tension. Extrinsic is clearly the amount of extracellular matrix. Intrinsic is the stiffness. So if the extracellular matrix is actually more stiff or less stiff in old and young subject. And we did it, of course, considering the amount of extracellular matrix. Our collaborators analyzed the amount of extracellular matrix on a group of subjects, showing a clear positive correlation between the amount of extracellular matrix, if you want, of fractional area occupied by extracellular matrix and the age. Since we want some numerical values for our finite element modeling, we made this linear correlation between the two, and in this way we were able to extract some numbers. In particular, we obtained that at 21 years old, we predict, if you want, the 3.3% of extracellular matrix over the cross-sectional area, which increased up to 8.2% at the 76 years old. Those are not clear number, of course, but we need it to make at least a first comparison in our finite element modeling. Okay, I think there is a open, okay. Yet now we have a way to also to obtain the intrinsic properties of the extracellular matrix, because leaving apart the equation, what we did was to consider the extra tension generated in young and old subject, and not by itself, not compared only to the cross-sectional area of the bundle, but on the cross-sectional area only of the extracellular matrix, which is higher for elderly and smaller for young. So given this value alpha, which is the one that we said before, we had the possibility to compare this parameter, which is a dimensionless parameter. So we took the total tension in the bundle, we subtracted the tension in average from the fibers, and we compared, we normalized it to the tension on the fiber, and we compared it to the amount of cross-sectional area in the extracellular matrix. And we obtained that actually the difference that we have observed in the wall analysis here disappeared, which means that is not the intrinsic properties of, at least in our experimental data, is not the intrinsic properties of the extracellular matrix which define the higher extra passive tension in elderly than in young subjects, but is mainly due to the increased amount of extracellular matrix. Here
5 minutes left.
Yes, I'm pretty close to the conclusion and then the perspectives. So conclusion is just for the experimental part, is that we observed that the resistance to elongation of fibers alone was not different between the two groups, young and elderly, while the extracellular matrix contribution was significantly increased in elderly. The proportion of muscle area occupied by extracellular matrix increased in our case from type 3.3 to 8.2 in from young to elderly, so more than double. And that this increase in the amount of extracellular matrix was enough alone to completely explain the increased passive tension generated in elderly than in young subjects. Then I can show you here some the perspective of what we can do now, and that what we are doing now, hopefully to present it in the next PaduaMuscleDays next year in person and not virtually, is that we can now, with the possibility, with the theory of continuum mechanics, we can include into our finite element modeling the properties, the material properties and the amount of extracellular matrix, analyzing how the, in this case, bundle of fibers behave differently in young and old subject. We do not have any data yet, but we already, just for this presentation, made some analysis for the Huijing experimental approach that I've shown before. So we allowed our bundle to contract with 4 over the 7 fibers considered. 4 fibers are contracting isometrically. 3 fibers of them can contract non-isometrically, so one of the side is fixed, the other one is free to move, but the extracellular matrix, of course, allow for the transmission of force also of those fibers to the wall force generated. What we obtained is that cutting about 1/3 of the cross-sectional area, the drop in tension is not of 1/3, is about 18%. Those are not definitive values. We are still working on it, but clearly we can somehow reproduce the experimental data. Okay, just the last 30 seconds for the acknowledgement for the people from our department, especially Professor Carlo Reggiani and Marco Nerici, and Michela Bondi and Elena Monti, which is who is a PhD student, but also from different departments, Professor Piero Pavan from Industrial Engineering, and Carla Stecco and her PhD student Cheng Lei Fan from the Department of Neuroscience. Okay, thank you very much for your attention, and I'm open for question or discussion.
Ciao Lorenzo, sono Feliciano.
Ciao, ciao Feliciano.
Just a brief question. Do you have any data on how the extracellular matrix changes before and after exercise, or comparing a group of non-exercise animals or human biopsies versus exercised?
So not yet, but I can say yet. I think Martino Franchi is also in the audience. This is a good question. This is probably the next step that we are planning to do. But still, we do not have yet this analysis. So we are interested in observe how extracellular matrix change it for exercise or not.
Do you think you can do this in animals?
Well, honestly, we started to try to analyze it in humans, and it's really in humans that there is a lack of information. Still, of course, animals is much easier to obtain data, and maybe if you have some something to give us,
that could be the chance to go in our collaboration.
Sure. It will be. I will be glad to continue this one. Yes, thank you.
Yes.
If I may comment, this is Marco Nerici. Congratulations, Lorenzo, for your presentation. If I may comment on Feliciano's question. Yes, muscle stiffness increases with training, and also tendon stiffness increases, and tendons being part of the extracellular matrix seems to confirm the hypothesis that the tension on the extracellular matrix increases with training. So muscle tendons become more stiff, and this is due to not only a slight hypertrophy of tendons, but mostly an improvement in tendon material properties.
Thank you.
I am not able to refrain to ask the usual question. Those differences could be just atrophy of the fibers?
No, I mean, we are here speaking
if
about
you add, sorry, if you add in your models just the mean size of your muscle or for your group of fibers, is this additional data relevant, or is the crazy idea of a crazy old people?
No, it's not a crazy idea, but if I, correct me if I'm wrong, but if I well understood, you are interested in the active force generation, right, from fibers, because here we are speaking about passively, and we extracted from the wall behavior the passive tension generated by the fibers.
We have not the dinner and lunch time to discuss. Yeah. It will be when you will be in Padua, maybe. And
yeah, sure.
I am obliged to go to the next speaker.
Okay.
I'm sorry to be kind.
Thank you very much. I stop my sharing.
Thank you. Congratulations.